several of you had a bit of struggle with. It's from the first assignment, which was on page 8, and it's problem 29. And paraphrasing just a tiny bit, really just simplifying what the question was, it says that we have a graph y equal g of x. And every straight line that's normal to that graph passes through the point 0, 1. Now, what can we learn about, or what does that tell us about the slope of y equal g of x? No, not the slope, the shape of y equal g of x. And the way the problem's stated, it kind of says, just discuss it and tell me what you feel and kind of guess what g of x would look like. And that actually, if you remember some high school geometry, can be done very well. But I want to go ahead and use some differential equations and see what we can find using things that we already know how to do. So let's just kind of start analyzing this with mathematical skills. So if we would, let's get a different color ink here. If we would think about the curve y equal g of x, then we would know that a normal to the curve, now let me just take a second here and remind you of what a normal of the curve would look like. So this is out of time here. Let's just say that this is some curve. I don't want you to think this is g, just some curve h of x. And if I pick any point on the curve, then we could look at the tangent line to the curve at that point. And the normal to the curve would be a line that goes through this point perpendicular to the tangent. Let me see how well I can draw that line. Well, I guess that's a passable perpendicular. So here's a curve, and here's the tangent to the curve at this point that we've kind of made big here. And passing through this point, but perpendicular to the tangent, is the line we would call the normal to h of x at this point. Now, since these lines are perpendicular, we know something about the slope. So we know that the slope of this line would be h prime of x, this as being a point x, y. And then the slope of the normal, they're perpendicular lines, so the slope of the normal would be 1 over h prime x. So let's put all of that in a box. I just want to do this because I think I can draw a box here pretty well. Well, that was kind of fun. So we'll just put that in a box, and that's an aside. It's something we already know, just a reminder. And so the normal always passes back to our problem here with g. The normal to g always passes through 0, 1, given in the problem. And the slope of the normal is negative 1 over g prime of x. But we also know another way to write that slope, the slope of the normal. So if I've got the normal here, so let's just say also here, also the normal goes through Well, it's got to go through x g of x because it touches the g curve at x g of x, and it goes through 0, 1 because that's given in the problem, that every normal to x to y equal g of x, every normal goes through 0, 1. So I've got 1 point, 2 points, and 2 points determine the slope of a line. So the slope is also, can you read that? Is also, here's one way to calculate the slope, but another way would be to use rise over run. So this would be g of x minus 1 over x minus 0, and this is also equal to the slope. So if these are both equal to the slope, it must be the case that g of x minus 1 over x, don't need to write that x minus 0, just write it x, is equal to negative 1 over g prime of x. Now, the graph is y equal g of x, and so I'm going to propose, so it would be easier and correct to replace g of x with y, just because it's easier. Don't have to do that, but it's going to make the writing a little bit easier. So if we do that, you know, then I want to think about what this looks like. Well, this looks like y minus 1 is equal to negative 1 over y prime times x. I'm going to do a couple other rewrites here. This would be y minus 1 dy dx, just multiplying both sides by y prime, is equal to negative x, or y minus 1 dy is equal to negative x dx. And you see where we're going to go with this next. Integral y minus 1 dy is negative the integral x dx. I think we're going to have to scroll just a tad here. So working from here, this is going to be y squared over 2 minus y is equal to negative x squared plus a constant. Now let's just keep working in this left to right fashion. This would be x squared over 2, my bad. Let's get rid of this 2 and this 2 by multiplying through by 2. And if I do that, I get y squared minus 2y is equal to the negative of x squared plus, now this is an arbitrary constant c. It's the constant of integration that we picked up right here. So if this is arbitrary, and if I multiply it by 2, what I've got is still arbitrary. So there's no reason writing 2c, and there's no hurt if you do it, but it's cleaner if you don't. So I've put this and left a space in right here, because what I want you to do is to think back to a long time ago when you were taking algebra and you used a technique called completing the square. You've got the first two terms of a trinomial perfect square here, and I want to add something to make this a perfect square. And so think about this. What if I would put a negative 1 right here? Isn't this then y minus 1 squared? That became y minus 1 squared. So that completed the square. Of course, if I'm going to put a negative 1 on the left-hand side, and I want to keep the equation balanced, which we always do, then I've got to put a negative 1 on the right-hand side. Now, what does this look like if I factor this? This looks like y minus 1 squared is equal to negative x squared plus c minus 1. And I'm going to ask you again, if c is an arbitrary constant, what's c minus 1? C minus 1 is also an arbitrary constant. So when I rewrite this, I'm going to replace that with just a c. C minus 1 is an arbitrary constant. So almost done here. Let's transpose this x squared, and we get x squared plus y minus 1 squared is equal to c. Now, that's the solution to our differential equation, not written as y equal, but written in, that's the solution, in implicit form. Remember Calculus 2, you learned how to take implicit derivatives. Maybe that was Calculus 1. In any case, it was some course in your background. So this is an implicit solution to the differential equation. And what does that solution look like? Well, again, you've got to remember back to some earlier work that you had in an algebra class. But if we had x minus h squared plus y minus k squared equal r squared, we said that was a circle, center, hk, radius, r. So what we have found here is that G is a circle, or the graph of G, maybe I should say, center 0, 1, radius square root of c. And c is an arbitrary constant, so we want this thing to be real, so c is going to have to be greater than 0, so it's not imaginary. But other than that, it really doesn't matter what the size of the circle is. And how would you have known that? Well, you might have remembered from a geometry course. Now this is with artistic license, a circle. If we start with a circle, and let's put its center right there, and there's a well-known theorem from geometry that says if you take any tangent to the circle, and from the point of tangency, if you draw a line that's perpendicular to the tangent, then that line will have to go through the center of the circle. And that's one of the ways in constructive geometry that you find the center of a circle. And in fact, that's a way that people that are turning things on a lathe find the center of a log that they want to put on the lathe. You take any tangent, take the perpendicular to that tangent, and that perpendicular will have to go through the center. So if you take two tangents and draw the perpendiculars to the tangent, what do we call a perpendicular to a tangent? It's a normal. So if you take two tangents, any two, doesn't matter which, draw the normals to those tangent lines, they cross somewhere, and where they cross is the center of this circle. So you could have done it from I remember this from high school geometry or college geometry, or you could do it with differential equations. But either case, it's a nice little problem. It's a lot of fun. It kind of gets us to thinking, and 15 minutes is my limit here. So I wish you all good morning, good afternoon, good evening, and take care of yourselves. Please stay safe, and we'll talk more in a bit. Thank you.